Okay, so we're going to calculate the pH of a acid salt here. So the compound of interest here is going to be NH4Cl. That's going to break into part in water to form NH4 plus and Cl minus. This Cl is the composite of HCl, which is a strong acid. And so we won't be interested in that one because the reverse process does not happen. But this is a composite of NH3, which is a weak base, so the conjugate or the backwards process will happen, so that's our species of interest. Here is the reaction. This is a conjugate process for the base NH3, so the the Kb associated with NH3 is equal to 1.8 times 10 to the negative 5. So we can use our equation that relates conjugate processes to the original weak processes. To find the equilibrium constant for the reverse process. And I get a Ka conjugate of 5.6 times 10 to the negative 10. So with that in hand, I can solve the equilibrium problem. Initial change equilibrium, and I'm starting with a 0.1 molar solution of this. I will have none of these. This will shift to the right as I have zeros over there, so these guys will increase by x. Everything's 1 to 1 here. This will decrease by x, and probably we can use our 100 rule. This k is very small, so if I do 0.1 divided by my k value, so this is concentration of reactants divided by k, 5.6 times 10 to the negative 10. This is going to be much larger than 100, equals 1.8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 1.8 times 10 to the 8, which obviously is bigger than 100. So we can use our 100 rule, which means our 0.1 minus x here. X is very small, so that's going to be approximately equal to just 0.1, neglecting the water because its concentration is constant. X are my equilibrium concentrations. So I can write my K expression for this conjugate process to be the concentration of NH3 times the concentration of hydronium divided by the concentration of NH4. That's x, and this is x at equilibrium. And this would have been 0.1 minus x, but we're just going to use 0.1 because of our 100 rule. 5.6 times 10 to the, I believe, negative 10, yep. And so we can solve here, 5.6, well, negative 10 times 0.1, square root, and we get a concentration of 7.48 times 10 to the negative 6. This is obviously much smaller than 0.1, so this was a very good assumption in this case. So now I'll get the concentration of my hydronium so that I can calculate my pH. And it works out to be 5.12. So that is how you can use your equilibrium calculation to determine the pH associated with a salt where one of the ions of the salt is a conjugate of a strong or weak base. And you can see here we get a pH that's pretty close to 7, and that's because this is a fairly weak acid. Only being the conjugate of a weak base means it's a very weak acid.